The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, guys, so let's get started. Welcome back from what I hope was an exciting holiday for everyone. So today we're going to talk about user authentication. And so the basic challenge that we want to address today is how can human users prove their identity to a program? And in particular, the paper that was assigned for today's class addresses sort of an existential question in the security community. Is there anything better than passwords for authentication? Right? So at a high level, it seems like passwords are a terrible idea, right? So they have very low entropy, right? It's very easy for attackers to guess them. Also, the security questions that we use to recover from lost passwords often have even lower entropy than the passwords themselves, right? Which also seems like a problem. And even worse, users typically will use the same password across a lot of different sites, right? So that means that the vulnerability in one password, if it's easy to guess, could expose a user's activity across a wide range of sites. So as the paper for today's class states, I love this quote, the continued domination of passwords over all other methods of end-user authentication is a major embarrassment for security researchers. Right? So the community is just seething out there. They want some better alternative. But it's not clear if there actually is an authentication scheme that actually totally dominates passwords, that's more usable, that's more deployable, that's more secure. So in today's lecture, we're basically going to do three things. So first of all, we're going to look and we're going to see how current password schemes work. Then we're going to talk about the desirable properties at a high level for any authentication scheme. And then we're finally going to look at what the paper gives us in terms of metrics for authenticating authentication schemes. And we're going to see how some of these other authentication schemes actually compare to passwords. So at a high level, what is a password? So a password is a secret that is shared between a user and a server. So the naive implementation of a password scheme is to basically just have a table, right, on the server side that essentially just maps usernames to passwords. Right? That's the simplest way you can imagine implementing one of these authentication schemes. User passes in their user name and their password. The server does a lookup in this table, compares the password that the client supplied, what's in here. If everything's good, the user is authenticated. So clearly, the problem with this is that if the attacker compromises the server, right, then it can just look at this table and then get all the user's passwords from the clue. Right? So that's clearly a bad thing. Right? So perhaps an improved solution is to have the server store a table that looks like this. So once again, it maps the username, but now it actually maps to hash of the password. Right? So the user client is going to supply their clear text password to the server. The server will then take that clear text password, hash it, do a lookup in the table, and once again see if the user is who he or she says that they are. So the advantage of this scheme is that by design, these hash functions are difficult to invert. Right? So if this table is lost, it's leaked somehow, or the attacker compromises the server, then the attacker can look at these things here, but it's difficult for the attacker to say, OK, this sort of string of random alphanumeric characters here, here's the pre-image that was used as the input of the hash function to generate that value there. So that at least is the nice thing about these hashes, sort of in theory. Now, in practice, attackers don't actually have to launch brute force attacks to figure out what the pre-images for these hash values are. Right? So attackers can actually take advantage of the fact that passwords, in practice, have skewed distributions. And by skewed distributions, I mean that, let's say that we knew that all passwords are 20 characters long. It's not like users actually pick passwords that sort of exist in all places in that space of 20 possible characters. In practice, people pick passwords like, 1, 2, 3. or Todd or things like this, right? And so in fact, there's been these empirical studies of how passwords work, and a lot of times these studies find things like the top 5,000 passwords cover about 20% of users. So what that means, in other words, is that if the attacker has a database of those 5,000 passwords, then the attacker can just hash those. And then when the attacker looks at this stolen password table, can just see if any of those things that come from this 5,000 large list match over here, right? And so empirically speaking, the attacker will be able to recover about 20% of passwords that way. And so folks at Yahoo found that passwords have roughly 10 to 20 bits of entropy, 10 to 20 bits of randomness in them. And that's actually not that big, right? So for example, if you think about, what might this hash function here be? So maybe it's something like SHA, something like this. So modern machines can actually calculate, millions of these hashes every second, right? So the fact that hash functions by design are supposed to be easy to calculate, supposed to be fast to calculate, combined with this fact that there are these skewed password distributions, means that in principle, this scheme here is not as secure as it might seem, right? So one thing you can imagine to try to make life more difficult on the attacker is you could imagine that you use expensive key derivation function. And so by key derivation function, I just mean this thing up here, this thing that's taking the password as an input and then generating something that's stored in the server. Right? And so what's nice about these key derivation functions is that they actually have sort of tunable cost. Right? So you can basically turn this knob and make that function run slower or faster, depending on what you want. And so the idea here is that let's say that you're going to use a key derivation function. So some of these examples are like PB, KDF2, or maybe bcrypt. You can look these up using the miracle of the internet if you care to know more about them. But the base idea is, let's imagine that one of these key derivation functions took a second to calculate, right, as opposed to a few milliseconds. That actually makes the attacker's job much more difficult, right? Because when the attacker is trying to, let's say, generate values for these 5,000 topmost passwords, it's going to take the attacker much longer to do that. So does that all make sense how these things work? Pretty straightforward. And so internally, these key derivation functions often operate by repeatedly calling a hash multiple times. So that's all pretty straightforward. So you might say, well, does this solve the problem? So can we just use these expensive key derivation functions and be done with it? So this is a security class question. The answer is no. So one problem is that the adversary can build something called rainbow tables. And so a rainbow table is basically just a map of password to hash values. And so the insight here is that even if the system is using one of these expensive key derivation functions, right, the attacker can calculate one of these tables once. Okay, it might be a little bit painful because each key derivation function invocation is slow, but the attacker can build this table once and then use that to crack all subsequent systems the attacker can break into that use that same key derivation function. Okay, so that's how rainbow tables work. And once again, to maximize the cost benefit of building this rainbow table, the attacker can take advantage of these skewed password distributions like we see up here. Right? So the attacker might only need to build a rainbow table for some small set of all possible passwords.
So salting makes this much more difficult.
Yeah, that's right. So we're going to get to salting, I believe, in a couple seconds. That's right. So, but at a high level, if you don't use salting, right, rainbow tables actually allow the attacker to spend some effort offline, calculate this table, and then sort of amortize the cost of calculating that table over breaking many different password databases. And so, right, so the next thing that we can think about to improve things is salting. I swear that guy was not a plant. I'll give you your $20 after class. So how does salting work? So the basic idea is that you just want to input some additional randomness into the way that the password is generated. right? So basically, you want to take this hash function, and you want to put some salt in there, which I'll explain in a second, and then the password. And this is the thing that you store on the server side of the table. So what is this salt? I mean, just think of it as just a string, right? A long string that's provided as sort of the first parts of this hash function, okay? So why is it better to use this scheme, right? And note that the salt is actually stored in the clear text on the server side, right? So you might be thinking, okay, well, if that salt is stored in the clear text on the server side, it seems like the server can both steal the table that maps usernames to passwords, and the attacker can also steal the salt. So why is that useful?
Because you pick the top most common password, you can't just use it once and find any user.
That's exactly right. So basically what this does is this prevents the attacker from building a single rainbow table and then using that rainbow table against all instances of that hash function, right? And so you can basically think of this as sort of uniquifying passwords, even if they're the same, basically. So this is what a lot of systems do in practice. They use this notion of a salt here. And so the best practices for this, so you want to choose a salt that's long, right? Because you can essentially think of the salt as adding more bits to this sort of pseudo password, right? And so more bits is always better. And the other thing you want to do too is that whenever the user changes his or her password, you typically want to change that salt too. So one reason for that is, let's say that users are lazy, right? And they want to pick the same password multiple times. Changing the salt will ensure that the thing that's stored in the password database will actually be different even if that password's the same. I think there was a question somewhere.
Yeah, why is it called salt?
I'm actually not sure why it's called salt. That's a good question. I'm sure there's some answer to this, though. It's like, why are cookies called cookies? The internet will know, but I actually don't know.
It does add some taste to the hash. You know, the hash is initially something, and that's the salt. You know,
there we go. I'm glad that we're getting this on film, because I feel this is how we're going to get our Turing Awards. That's right. So yeah, I'm sure there's some answer out on the internet, so I'll look that up later. But does that all basically make sense? Okay, so these approaches are fairly straightforward. All right, so what I've assumed so far is that somehow the client is transmitting the password to the server, but I haven't actually specified how that transmission is actually going to take place. So, are there questions? No? Okay, so yeah, how do we transmit these passwords? So, you know, the first idea you might have would be, well, we'll just send the password in the clear over the network. This is clearly cartoonishly bad, right? Because then there could be a network attacker who's basically snooping and seeing the traffic that you're sending, and that snooper can just take that password right off the wire and then impersonate you. Okay, so we always start with a straw man before I show you other straw men, which of course are also fatally flawed. So first thing you think about is sending the password in the clear. Another thing you might think, which would be a little bit better perhaps, is perhaps we send the password over an encrypted connection. Right, and so we use some type of cryptography here. Maybe there's some secret key or something like that, and that's what we use to transform the password before we send it over the connection. So at a high level, you know, encryption always seems to make things better, right? Trademark. But the problem is that unless you think carefully about how you're using things like encryption and hashing, you may not be getting the security benefits that you think that you're getting. Because, for example, what if there is someone who's sitting between you, the client, and the server, this proverbial man-in-the-middle attacker, right, who's actually snooping on your traffic and pretending to be the server, right? If, when you send encrypted data, you haven't actually authenticated the other end, right, then you could still be opening up yourself to problems, right? Because if the client just, you know, let's say picks some random key, sends it to some entity on the other side who may or may not be the server, if it's not the server, your encryption didn't really buy you anything, right? You're just sending something to some person who will then be able to get all your secrets, right? And so similarly, people might think, oh, well, what if I don't send the raw password, but I send the hash of the password instead? That actually doesn't give you anything in and of itself either, because whether you send the password or the hash of the password, I mean, the hash of the password has the same sort of semantic power as the original password itself, right? If you haven't authenticated the other side, if you haven't authenticated the server, or things like this. So the basic point with this discussion here is just to sort of stress the fact that just adding encryption or just adding hashing doesn't necessarily give you any additional power, right? If the client can't authenticate who he or she is sending the password to, then the client could be mistakenly divulging that password to someone that they don't intend to divulge it to. Okay, so perhaps a better idea than these two is to use what they call a challenge response protocol. And here's an example of a very simple challenge response protocol. So let's say we've got the client here, and then we've got the server over here. So the client says, hi, I'm Alice. And then the server responds with some challenge scene, right? Some quantity that the server got to pick. And then the client is going to respond with the hash of that server sent challenge, and then you can concatenate that with the password, right? So at this point, the server can take this quantity. The server knows the challenge that it sent, right? And presumably the server knows the password. So the server can sort of recompute this quantity and see if it actually matches what the user sent, right? So what's nice about this protocol is that if we ignore man-in-the-middle attacks for a second, the server is now confident that the user is actually Alice, because only Alice would know this password here. And what's nice about this is that if the server is actually the attacker, right? So in other words, if Alice sent this thing to someone who's not the person that she's trying to authenticate to, then the attacker still doesn't know the password, right? Because the attacker got to choose C, but the attacker doesn't know what this is. And so basically for the attacker to figure out what the password is, the attacker would have to be able to, once again, sort of invert these hash functions, right? You have a question?
I'm just curious. How do you you don't make the client do the hashing?
How come you don't?
JavaScript to make it do the PBKDF2 hashing. Also increases the load in the server. And also that way the server definitely doesn't know what the password is. So it's like an extra perk that you gain.
So let's see. So your proposed scheme is that the client side is going to call this thing.
Yeah. So instead of sending the password and having the server hash the password and check it, you'll just the client will just send the hashed password.
The client will just send the hash password. So one thing you want to keep in mind is that you typically, well, so there's a couple of reasons. So one reason, as we'll discuss later, is that there's going to be these things called anti-hammering defenses. Right? Anti-hammering defenses are designed to prevent sort of like a bad client from continually asking, is this the password, is this the password, is this the password? Sometimes as a result, it's easier for things to be done on the server side as on the client side. But suffice it to say that you can, in fact, do the hashing on the client side, right, using JavaScript or something like this. But the basic idea is that somehow you have to have the computational expense be very, very large, right? Because that's going to prevent the attacker from just guessing sort of what the password is quickly. You have another question?
Well, I just wanted to point out that if the client does the hashing, then it's as if you're not doing hashing, because your password is the hash.
So that's true, right?
So if someone gets the sort of table from the server of all the usernames and hashes, they can log in.
That's right. That's right. Yeah, it gets a little bit subtle sometimes, depending on who can pick, for example, these challenge values, right? Because if clients and servers can pick challenge values, sometimes that makes it more or less difficult for the client to launch those types of attacks. So, for example, like one problem with this protocol here is that basically the client doesn't get to inject any randomness into this, right? So you can imagine that we can make this protocol more difficult for the server to invert if the client actually got to choose some challenge that was put in here. So you get like a server-side challenge versus a client-side challenge. But you're right about that. Any other questions? Okay. So this segues into the discussion we were just having. So even though to break this, the server would have to invert this hash, the attacker could still try to do one of these sort of brute force attacks, right? So one way that we can prevent the server from doing these brute force attacks is to choose one of these expensive hash functions, kind of like we were discussing before. Another thing, as we just discussed, is that you could actually allow the client to, for example, choose its own client-chosen challenge over here. And so that essentially would act as like a client-chosen salt, right? So that would essentially make it more difficult for the hacker to do things like build up a rainbow table. Because note that if the server is the attacker here, the server always can pick the same challenge value again and again and again, right, allowing it to build up a rainbow table. But if when the client responded back, the client also included some salt, right, some client-chosen challenge that it included, then that will prevent the attacker from building one of those rainbow tables. So does that all make sense? OK. So yeah, so one thing that I mentioned is that might be useful to do is implementing these anti-hammer defenses. And so anti-hammering defenses are basically designed to rate limit the number of password guesses that sort of a bad client can issue. Right? Because the idea here is that if you've got some client who's trying to launch one of these sort of brute force guesses against the password, you don't want that client to be able to sit there in a tight loop and just say, is this the password, is this the password, is this the password, is this the password? Right? So one way you can do anti-hammering is, like I said, just do that rate limiting. So the server will say, I will only accept, let's say, 3 password guesses per second from any particular client. Right? You could also imagine implementing timeouts here. Right? So maybe the client can issue a bunch of password requests in a row, but then after, let's say, 10 of them are wrong, the server says, OK, you got to hold on. I will not accept any more requests from you for, let's say, 10 seconds, something like that. Right? And so both of these things are designed to prevent against brute force attacks. And so, for example, like some smart cards have these types of defenses. Some TPMs have these kinds of defenses, right, to basically stop against this brute force attack. So why is it important to use these anti-hammering defenses? Well, one reason why it's important is, as we discussed, these passwords have so little entropy. Right? So because passwords typically have so little entropy, it's really important to prevent the attacker from just trying to cycle through that low entropy space very, very quickly. So as you may be aware, a lot of websites have these formatting constraints that push upon you for your password. They'll say things like, oh, your password must have, an unprintable, not an unprintable character, but it must have like a punctuation. It must have a mixture of numbers and letters. You must have like uppercase and lowercase stuff, so on and so forth. And so what those constraints are trying to get you to do is they're trying to get you to expand the entropy of the password. But what's problematic, though, is that it's not really these formatting constraints that we should be caring about. It's the actual entropy of the password itself. Right? So as it turns out, even if people are given these constraints, like you have to use punctuation characters and stuff like that, the entropy of the resulting passwords is often quite low. Right? So for example, people will often put punctuation at the beginning or the end because they don't want to be troubled to remember, like, do I have like a $ in the middle of something? Right? And so as it turns out, these formatting requirements oftentimes don't make dictionary attacks much harder for a sophisticated adversary. Right? And the reason is because basically the dictionary attacker can leverage these observations about how people pick passwords, even in the presence of constraints. Right? So for example, if the attacker knows that people typically put punctuation at the beginning and the end, just incorporate that into your dictionary attack. Right? And so there's actually a really interesting website you can go to that's called Telepathwords. And so what's neat about this site is that you can it has a little text box, right? You can type a character into that text box. You're pretending that you're entering a password. And Telepathwords will try to guess what your next character is. Right? It's like as you type additional characters, it'll have a little drop-down box which says, where are you going to put this? Where are you going to put this? And it'll give you a little, like a little blurb that says, here's why I think that you were going to enter this next password. So how does Telepathwords work? So it basically has a bunch of databases, right? It has a database of common passwords. It also has a list of popular phrases that it's taken from websites. And then it also has this set of heuristics which describe common user biases in picking passwords. So for example, one funny bias is that people will often, like when they're forced with these constraints to say you must use punctuation and stuff like that, a lot of times they will, when they're picking characters for the password, they'll use keys that are adjacent to each other. Right? So in other words, there'll be very small edit distance in physical space with respect to edit distance sort of in the actual password itself. So what telepassword does is it has this big database here. So when you type in things, it's running these models and it's saying, statistically speaking, here's the most likely thing that you're going to type next. It's almost like autocomplete for passwords, right? And so what's funny is that this shows, once again, that if you have these constraints, they actually don't protect you that much if there are still these underlying sort of a priori distributions of things that the attacker can leverage. And if there was a question?
Oh, yeah. So it seems like if an attacker is too sophisticated, that they could, try guessing like the user's password from a bunch of IP addresses and things. And the only way to sort of prevent hammering in this case would just be to have like a global rate limit on password equals to the user's account.
Yeah.
But then you have like this issue of like, DOS possibility against the legitimate users and what's like. So how do you like balance?
Yeah, it's very tricky. That's a good point. So anti-hammering, I mean, it basically comes down to what's the scope of the attack that you're trying to prevent, right? So if you're concerned about sort of distributed attackers and sort of a network system, it does become very, very subtle. And suffice it to say that the notion of anti-hammering distributed systems, and also the notion of things like, let's say, click fraud, for example, so in other words, how does someone who's running an advertising campaign online determine if someone's actually clicking the link and I should actually be paying someone for those clicks versus this is just some spammer who's got some bot that's just sitting there clicking on stuff, right? So suffice to say, there's a lot of distributed heuristics that try to solve those problems. And in many cases, it's not a science, it's an art. But you're exactly correct that in the distributed setting, things get much more difficult. All right, so does this all make sense? Yeah?
What about the cryptographic anti-hammering defenses? So most of the time you're not sending a hash on the line, and these hashes are at a pretty high rate. And what you get out of it is exactly what you need. You get either the password or the hash of the password. So is there, like, I know there are protocols like SRP, or there are some zero-knowledge protocols.
Yeah,
do those
so
get used in practice?
They do. Those things are, so yeah, those protocols provide some stronger cryptographic guarantees. A lot of times they are not backwards compatible with current systems, which is why in practice you don't see them used a lot. But yeah, so there are some protocols, for example, that that allow the server to not have sort of any notion of the password at all, right? So there's some zero knowledge type thing or whatever. So those things do work in practice. But like one of the things that this paper says is very interesting is that they basically go through all these authentication schemes and they say, okay, here's passwords, yeah, they kind of suck. Here's some other things that are actually much stronger on the security axis, but then they all fail on like deployability or usability or things like that. And so that's sort of one of the interesting and slightly sad outcomes of this paper, that maybe even though we have all these sort of much stronger from the security perspective protocols, we can't deploy them for some usability reason or some sort of technical reason. Okay, so that's just a fun site to go to, right? And so they claim that they don't store your passwords, so you can take them at their word if you want to. But it is very interesting to just sit down and think, like, what password would I generate, and then type into this and see how accurate it is in guessing what the next thing will be, right? And it even covers things like the popular heuristic, like take a popular phrase and then that has multiple words, and then only take like the first letter of each word. So this thing is very, very good, very, very scary too. Okay, so that's telepathwords. And so one thing that is also interesting to think about is, in your password scheme, is it vulnerable to offline guessing? Right, so this was a problem that Kerberos v4 had, and then also v5 without this thing they call pre-auth. So the basic idea is that in these versions of Kerberos, anyone could ask the KDC for a ticket that would be encrypted with the user's password, right? So basically, the KDC did not authenticate requests that were coming from a client. Now, the thing that the KDC would return was, in fact, there is some set of bits here that the KDC would return. I'm sure you don't want to think about this ugly set of cryptographic parameters anymore, but suffice it to say the KDC would return this stuff that was encrypted with the key of the client, right? That's what will come back to the client side. So the problem with this is that because the server did not check who it was sending this encrypted set of things to, the attacker can basically get this thing here and then try to just guess what KC is, right? Just guess that KC is some value, try to decrypt this, see if it looks reasonable. If not, try to guess another KC, decrypt this, see if it looks reasonable, right? And the reason why the attacker can launch this type of attack is that this thing here, this TGT, actually has a known format. So it has things in here like timestamps, and it has things in here like various length fields which have to be sort of internally consistent. And so that basically helps the attacker, right? Because if the attacker guesses a KC, gets this thing here, a decrypted thing, and the internal fields don't check out, the attacker knows that it picked the wrong KC, so they can go on and pick another KC, right? And so in Kerberos v5, basically the client has to send, in this thing that it sends over to the KDC, it basically sends a timestamp, and then this timestamp is going to be encrypted with KC, right? So this is sent to the server, and the server looks at this and validates that before it will send something back to the client, right? So that gets rid of this problem that any random client can show up and just ask for this thing here. All right.
So is the timestamp included in the message? So can't an attacker just get this message and brute force it?
Let's see here. So can't the attacker get this message here?
Yeah, the encryption.
So you're worried that an attacker might try to spoof this, for example, or?
No, I just brute force it and get KC out.
Okay. So in other words, you're worried someone could observe this.
Right.
The attacker could observe. Right. So I believe that this is put inside an encrypted thing that belongs to the server, whether the key belongs to the server, I think, to prevent that attack. I have to check the protocol, so don't quote me on that. But you're correct that if it's not, for example, and if the attacker, for example, knew something about what the current time is, roughly, that actually is super useful, right? Because then the attacker can guess, oh, the timestamp should be roughly between here and here, right? And if it sees this in the clear, it can do the exact same attack that we had up here.
It's a little better because the attacker has to be in the middle, but it's still susceptible.
That's true. Well, yeah, that's right. I mean, the attacker has to be on the network somewhere sniffing stuff. That's right. All right, so that's offline guessing. So another thing that's important to think about is sort of password recovery. So this is the idea that you lose your password, and then somehow you have to go to the service and you have to ask for another password, right? But before you get that password, you have to prove that you are you in some way. So how does that work? How do you do password recovery? So what's interesting is that people oftentimes focus on the entropy of the password itself, right? But the problem is that if the password recovery questions or the password recovery scheme has low entropy, that actually affects the entropy of the overall authentication scheme, right? So in other words, the strength of the overall scheme is basically equal to the minimum of the password entropy and the recovery question entropy. And so you see this actually play out in a lot of real-world scenarios. So there's a lot of famous cases, like the Sarah Palin case, where basically someone was able to recover her password fraudulently because her recovery questions were things that any random person could find by looking at her Wikipedia article, for example, find out where she went to high school and things like that. And so oftentimes these password recovery questions are not very good. And they're not very good because of a couple of reasons. So sometimes these things just have very low entropy, right? So if you have a password recovery question that is something like, what's your favorite color, right? The most popular answers are going to be like blue and red. Nobody's going to say like off-white, fuchsia, magenta, right? So some of these recovery questions just intrinsically are just very difficult to provide a lot of entropy for. The other problem is that so sometimes these recovery questions can be leaked via social media. So for example, one of the recovery questions is, what's your favorite movie? So maybe the space there is a little bit bigger. But if intrinsically I can go look at, let's say your IMDb profile, your Facebook profile, and figure out like, oh, hey, you literally told me that's your favorite movie, this isn't super useful either, right? And another problem, this is actually sort of the funniest one, is that the user-selected recovery questions are often super weak. So for example, people have done a survey of what some of these questions look like, and sometimes users themselves will set recovery questions that are things like, what is 2 plus 3? Right? And so that's, at the time, the user's thinking this is a big hassle, never going to have to use this, but trivially, most humans who pass the Turing test can answer that question successfully, and then therefore get the user's password back.
So both Microsoft and Google have a scheme for recovering passwords that doesn't use any recovery passwords for recovery questions. It's basically like you enter in your name and maybe the subjects of some emails that you've sent, with a small amount of additional information. Based on that, in some cases they can So
that's right.
The security of that kind of stuff then looked at?
So I don't know of any formal study like that. Those things are actually a lot better. So I actually know this because I was trying to help a friend go through this process. So she basically lost control of her Gmail account, and she was trying to prove that this was her account. And so yeah, they would ask you things like, roughly speaking, when did you open this account? Roughly speaking, before you lost control of this account to Hezbollah or whatever, who are some of the people that you talked to? And things like that. And it's actually a pretty laborious process, right? But what ends up happening is that you're exactly correct. It ends up being much more powerful than this stuff, right? And so, like I said, I don't know of any formal studies of that, but it does seem, at least intuitively, to be much stronger than these types of things. All right, any other questions? OK, so yeah, so now we can get to sort of the paper for today. So in the reading for today, the authors basically propose a bunch of factors that can be used to evaluate these authentication schemes. Right? And what's really cool about this paper, I think, is that it basically tries to say, look, a lot of us in the security community are sitting there kind of fighting just based on aesthetic principles. We should pick this because I just like the way that the curly braces look in the proof. We should pick this because it just uses a lot of math mode, right? And so what they say is, well, look, why don't we try to establish some type of criteria? Maybe some of the criteria are a little bit subjective, but let's just try to have this taxonomy of ways to evaluate these authentication schemes. Then let's just see how these various schemes stack up. And so the authors basically propose 3 high-level metrics for evaluating these schemes. So the first metric is usability. And so the base idea here is how easy is it for users to interact with this authentication scheme, right? So they define a couple interesting properties. So for example, is it easy to learn? This basically just means, is the scheme easy to learn? Right? So some of these categories are pretty straightforward. Some of them actually involve a little bit of subtlety. But this one makes a lot of sense. And so if we look at passwords sort of pass this test, right? Because everybody is used to using passwords, so we'll say that they're easy to learn. Another category is infrequent errors. So that means when you are trying to authenticate to the system, if you are the actual user in question, is it the case that you can often authenticate yourself without generating errors? And so here, the authors say quasi-yes. And so the quasi prefix is one of the more entertaining aspects of the paper, right? Because the authors kind of admit there's this element of subjectivity to it, so we can't necessarily say with crisp precision, yes, no, things like this. So the reason why they say quasi-yes is because in general you can authenticate a password successfully. But we've all been in that place where it's like 3 a.m., we're trying to log into our email server, our mind's not in the right place, and we enter a bunch of errors a bunch of times, right? So they say quasi-yes for this. Another category is scalable for users. And so the basic idea here is if the user has a bunch of different services that he or she wants to authenticate to, does this scheme sort of scale well? Right? Does the user have to remember some new thing for each one of these schemes? And so for here, the authors say no. Right? Because in practice, it's very difficult for users to remember a separate password for every single site that they go to. This is one reason actually why people reuse their passwords often. So another usability property is easy recovery. So what happens if you lose your authentication token, in this case your password? Is it easy to reset? And in this case, the answer for passwords is yes. And in fact, they are probably too easy to reset, as we just discussed a couple minutes ago. So that's a yes. And so another interesting one is nothing to carry. So a lot of the more Baroque authentication protocols require that you run some smartphone app, or you have some security token or a smart card or things like that. So that's a burden, right? Maybe not with a smartphone so much, but having to carry around one of these other gadgets is probably a pain. And so this is actually one nice feature of passwords. You basically only have to carry around your brain, which presumably you should have at all moments. So that's basically what usability looks like, right? And it's just very interesting at a high level that a lot of times, these sort of factors are given a little bit of a short shrift in the community, security community, when people are evaluating new schemes. They say, oh, this thing uses like 1,000,000 bits of entropy and can only be broken by the Death Star or whatever. But then people don't necessarily remember, oh, these are actually very important factors too, right? Okay, so the next sort of high-level category that the authors use to evaluate past authentication schemes is deployability. So the base idea here is how easy is it to incorporate this system into current web services, right? So one thing that they look at, for example, is it server compatible? And this basically means, can I easily integrate this scheme with today's servers, which are based around sort of text-based passwords, right? And so since success here is defined with respect to passwords, passwords succeed. So another metric is browser compatibility. Similar type of thing. Can I use this scheme with current off-the-shelf browsers without having to install a plugin, something like that? Once again, passwords win by default. And another interesting one is accessibility. So can people who can use passwords now, but maybe have some type of physical disability, maybe they're blind or they can't hear well, or they can't gesture well, or things like that, can they actually use this scheme? Right? And this is actually pretty important. So once again, the authors say yes. It's a little bit weird because it's not clear that all people with all disabilities can use passwords, but they say yes here. So these are sort of three interesting things to think about with respect to deployability. And the reason why this deployability category is so important is because it's very difficult to get anyone to upgrade anything ever, really, right? I mean, people don't even want to reboot their machines to get a new OS update installed. So it's very difficult if the scheme requires reasonable changes on the server to sort of get people on the server to actually do different stuff. This gets back to your question, why don't we use these better things? Because deployability in many cases is super, super important to keep that. All right, so then the final category that people look at is security. Right, so what kinds of attacks can this scheme prevent? So a lot of these security properties are sort of resilient to foo, right? So I'll just sort of shorten that with res. So is the scheme resilient to physical observation? Right? So the idea here is that an attacker cannot impersonate a user after observing them authenticate a few times. So imagine that you had a shoulder surfer, so you're somewhere in a computer lab, someone's looking over your shoulder, seeing what you type in. Imagine someone's videotaping you. Maybe someone's got a microphone, they're listening to sort of like the acoustic signature of your keyboard and trying to extract things from that, so on and so forth. So the authors say that passwords actually fail this test, and that's because if someone can videotape you typing in things, they can pretty easily figure out what letters you typed. Or there's actually these attacks where you can actually listen to the acoustic fingerprint of the keyboard and detect what was typed based on what sounds that you hear. So passwords are not resistant to physical observation. So another property is resistant to targeted impersonation. And so the basic idea here is that, is it possible for someone who knows you, a friend, an acquaintance, a spouse, a loved one, a family member, whatever, to impersonate you using their knowledge of who you are and what you do, right? So could your friend try to pretend to be you easily in this particular scheme? So here, the authors basically have another one of these quasi-yeses. And they say quasi-yes because they're not aware of any studies which show that if you know a person, you're more likely to be able to guess their password. So they say quasi-yes for that. And so note that resistance to targeted impersonation, this is where most security backup questions fail miserably, right? Because if someone knows something about you, quite easily they can sort of guess your security questions in many cases. All right, so then we have two categories that involve guessing. So the first one is resilient to throttle guessing. And so what this means is if the attacker cannot issue guesses at line rate, because, for example, the server uses anti-hammering mechanisms, is the scheme safe against the attacker, right? And so here they say no, right? And so the reason why they say no is because in practice, passwords not only have sort of low inherent entropy, right, because they're not that long, but also they have that skewed distribution, right? And so what that means is that even if the attacker is throttled in some way, typically the attacker can still make good forward progress and crack a lot of people's passwords. So they define another guessing property, which is resistant to unthrottled guessing. And so this is basically saying, suppose that the attacker can issue these authentication forgery requests as quickly as he or she wants, right? So in other words, the attacker is only limited by the speed of their hardware. So is the authentication scheme resilient to that type of attack? And here, this answer is also no, for the same reason that the answer was no up here. So basically, passwords have a very small entropy space, and they come from the skewed distribution. So that's all pretty straightforward. One interesting one is resiliency to internal observation. So this means that the attacker cannot impersonate a user by intercepting that user's input. For example, by installing a keystroke logger on the keyboard that the user is using and using that logger to steal key presses, right? This also means, for example, that there's no way for a network attacker who's observing the things that the client's sending over the wire to use that knowledge of the network traffic to later impersonate the user. And so here they say passwords do not have this scheme. And they essentially say it's because passwords are static tokens, right? They don't change. And typically static tokens are vulnerable to replay, right? So if somehow, for example, an attacker installs a keystroke logger and gets your password, then basically the attacker can use that password until it's either expired or revoked or something like that. It can just replay it again and again to that authenticating server on the other side. So here passwords actually fail that test. Another thing that we've talked about a little bit in this class, phishing. So resilience to phishing is another security metric. And the basic idea here is that if the attacker can simulate a valid service, for example, by attacking the DNS infrastructure or something like that, then the attacker cannot collect credentials from the user that the attacker can then use to pretend to be the user later on. And so this basically is supposed to penalize sites that do not strongly tell the user, hey, I'm this particular service, so you can feel confident to give me your credentials. And so here passwords fail just because phishing sites are very, very popular. So passwords don't really intrinsically provide any protection against that. Now the next two are particularly interesting in the context of a large-scale distributed system. So no trusted third party. This essentially means that other than the client and the server, there's no one else in the system that is sort of involved in the authentication protocol, right? And so that means that there's no third party who, if that third party were compromised, the entire integrity of the security scheme might fall apart. And so this is actually an interesting property to look at because a lot of authentication problems would go away if we could just store all of our authentication information in one place, right? We just store it in one place. It's very simple. We don't have to remember a lot of stuff on the client. We just say, whatever service you want to use, you always go to this one third party, and that third party will also always be able to sort of authenticate you and then allow you to go on your merry way. Now, of course, third parties are problematic from the perspective of robustness, right? Because if you do have one of these global third parties that everybody trusts, if that third party gets subverted, then perhaps the integrity of all the sites that use that third party to authenticate, all those sites are potentially in danger. So they say that passwords do not have a trusted third party because each user is forced to have a separate password for each site. A related property is